So the main focus of today is to focus on, or is to talk about salts that have limited solubility in solution. So like when we've been making our buffers and things like that, all of the salts presented to us, we have assumed have 100% ionized that help us get the component of the buffer that we need, for example. So now we're going to focus on salts that don't 100% ionize. In fact, they generally precipitate out of solution. This is a new slide in the notes if you had printed them, okay? Um, so all sodium, potassium, ammonium, those salts are always soluble. So if you remember from your solubility rules, you need to remember like nitrates are always soluble, ammonium, and then all of your alkali metals. Those are like the main ones that you need to know. And then all of the rest you would know by default. And I'll show you what I mean when we practice. So our insoluble salts, instead of doing a one-way arrow now, are going to go to equilibrium. So because they only ionize slightly, we write them with an equilibrium arrow instead of a one-way arrow. And because of that, we can write an equilibrium expression for them. So write K equals products over reactants raised to their respective coefficients. Now, if you have, for example, silver chloride is very limited solubility in solution. So it breaks apart a tiny, tiny bit into silver ion and a tiny, tiny bit into chloride ion. But in fact, most of it stays intact as a solid. So if you go to write the K expression, K equals products over reactants, you notice you don't see a denominator because your reactant is a solid and you don't include solids in equilibrium expressions. So really, the Ksp expression is based on the ions of the solution, or ions of the substance. Something that I want to mention, and I'm going to make this up, this is not true, but we haven't done this in a while because we've been working very heavily with 1:1 to 1:1 ratios for a pretty long time. So I want to refresh our memory. If this substance had broken down, let's say there were 2 chloride ions in it, where would that 2 go in my expression? Exponent, right? I'm just refreshing because we haven't worked with things that weren't 1:1 for a long time in writing equilibrium expressions. And then I also want to briefly mention, if you were to do an ice chart, let's say for this, if you called silver ion X, what would you call chloride ion? 2X, right? Because there's double of it. Right, this is not true for this species, but if it was, if you had to call this X, you would call this 2X. You wouldn't want to call this X. I mean, you could, but if you called this X, you'd have to call this 1/2 X. And I just don't like fractions, so I choose not to do it that way. It doesn't mean you can't do it that way, just I don't like to do it that way. Okay? All right, so you see now we have an equilibrium expression that isn't involving a weak acid or a weak base. It's involving a salt. You could think of it like a weak salt. I don't know that's the best way to think of it. It's really just a salt with limited solubility. You can't get a lot of it to ionize, and so that's why it goes to equilibrium. Okay, so all of these problems, these KSP problems, involve salts with limited solubility. So you're never going to see like a KSP problem, most likely for like sodium nitrate. Sodium nitrate is pretty soluble in solution. So you wouldn't see a problem like that with that kind of salt. It's going to be salts that generally like you would see that would be common to precipitate out of solution. So speaking of that, we're going to go back and do a little bit of review. And we're going to dust lots of cobwebs off right now. Net ionic equations. So I want to talk about these salts that have limited solubility. So this is old stuff, very old stuff. So we're going to work through it together. So I tell you solutions of silver nitrate and magnesium chloride react. And then I tell you a precipitate forms. So the first thing I'd like you to do is see if you can write out the reaction, predict the products, as well as balance. So it's been a long time since you've done this. You have to know how to do it, so this will be a nice review. A helpful thing to do is this. And then I would like you to try it before I start working through it. Is this correct? What state of matter are my reactants? Solutions imply aqueous. Now, it is your job to know that nitrates are always soluble. You have to know that as a product. Nitrates are always soluble, so this is going to be aqueous. So if I tell you a precipitate forms, by default, you know it has to be this guy. Now, there are some problems. My reactants are written perfectly. My products are not. What is wrong? 2. Perfect. Magnesium's +2. Nitrates -1. You better have 2 nitrates. You cannot just go with what's over here. When you switch partners, you have to reevaluate their charges with their new partners. So the same thing here. Silver is +1, chloride is -1. I don't need 2 chlorines. Silver's +1, chlorine's -1. Again, you have to reevaluate when they have new partners. Why are there 2 chlorides over here? Well, because its partner is magnesium. Its partner's not magnesium anymore. You have to reevaluate their charges. Now, you go, well, what about this too? Well, that's why we balance reactions. So, let's go ahead and balance. And this is my beautiful molecular equation. So now let's refresh. We're going to refresh net ionic equations. So there are 2 rules for, there aren't 2 rules. Net ionic equations, there are 2 things that have to happen before you can break apart a substance into its ions. The first thing is it has to be aqueous, okay? You cannot touch solids, you cannot touch liquids, you cannot touch gases. It has to be aqueous. And the second thing, it also has to be strong. Strong acid, strong base, strong electrolyte. All of our salts are considered strong electrolyte, aka ionic compounds. And I don't have acids or bases in here. These are all salts. So I don't have to worry about like a weak acid or a weak base. Remember, you do not get to ionize weak acids or weak bases. Okay? So aqueous and a salt, aqueous and a salt, aqueous and a salt, not aqueous. So I'm going to break apart everything I'm allowed to. So let's do that. So don't forget about the coefficient out in front. It gets distributed to both ions. Remember that 2 comes out in front. Sorry, I kind of ran out of room. So this is called your complete or your gross ionic equation. You break apart everything you're allowed to. And then the net ionic is when you do what? You get rid of your, do you remember what they're called? Spectator ions. Beautiful. So that would be nitrate right here. 2 nitrates as a reactant, 2 nitrates as a product. Magnesium reactant, magnesium product. And the net ionic is what's left over. So I have this guy left that I haven't canceled out, and this guy, and this guy. So here we go. Is this correct? This is wrong. You don't get to just get rid of charges because you feel like it. Where'd the plus go? Where'd the minus go? You have to include them. If you write 2Ag plus, that means it's an ion. If you write 2Ag, it means it's solid silver. It's not the same thing. So there's the net ionic. Now you can reduce this because everything's 2, 2, 2, so it could just be 1, 1, 1, where you have silver ion and chloride ion forming silver chloride, which is obviously a salt with limited solubility. As you can see, it's predicted to be a solid. Now, what state of matter are all ions? All ions are always what state of matter? Aqueous, okay? So, having said that, give me one sec. All right. Here we go. Silver nitrate. It's aqueous, right? It looks like a liquid. It kind of stains. That's why the bottle kind of looks dark. It stained my fingers too. You can see it stains a little bit, but this is a colorless aqueous solution. Silver nitrate. I got a test tube. Good. Okay. Magnesium chloride. Aqueous. Solution. Colorless. These both look like water. They're not water. Don't drink them. Okay? Now, I just said I should get a solid, right? If I mix these two, that's what we just said. So, let's find out. Ready? Can you see through here anymore? No. That's because there is solid in there. A ton of it, actually. Well, maybe not a ton, but a lot of it. Now, it's hard because it's floating around, but after it takes some time to settle, the solid will precipitate out to the bottom because it's more dense than the solution. Okay? But for sure, a white silver chloride as a white precipitate has formed. All right? I have my one, I did this yesterday as well. So you can kind of see after it sits for long enough, you can see that solid form in the bottom, and then the aqueous unreacted ions are just sitting up on top of it. Okay? So this will eventually look like this once it gets a chance to settle out. So I definitely produced a precipitate. Silver chloride has limited solubility. That's why it's sitting in the bottom of this test tube. And it's actually, you can kind of see if I go up close. Let's see. You can see it like down in here, right? Sorry, I know it's like kind of blurry. Okay. So now, I would like you to try this one. All right. This is what you got. So again, if I tell you a precipitate forms, and this will be just kind of like how the College Board presents it as well, nitrates are always soluble. So you know it can't be this guy. It has to be by default the other guy. The other rule is alkali metals are always soluble as well. So sodium's an alkali metal. And remember, again, I'm going to reiterate, those solubility rules that we're talking about right now are for predicting the states of matter of products only. Reactants will have to be told to you what state of matter they are. Okay? So it's very apparent that lead 2 iodide obviously has limited solubility in solution. And in fact, if lead ions come into contact with iodide ions, you should see a solid precipitate form of lead 2 iodide based on our prediction. So test tube. Lead 2 nitrate. Solution, aqueous. Yeah? All right, let's get some. I'm going to use a pipette to do this. This thing. That's good. Aqueous solution. It's even colorless. Okay. And then I also have sodium iodide right here. Okay, aqueous solution. All right. And we're supposed to get a precipitate, right, when I mix them. Ready? That's a yellow precipitate. It's crazy, right? Okay. Now, again, you can't see through it, so you know there are solid particles obviously in here. I do have the one that I have from the last couple of days that I'll show you in just a second, but lead 2 iodide is a yellow precipitate. It's obviously not very soluble in solution, as you can see some solid has formed when I mixed them. Okay, from yesterday, let's see if there's a better one. After it's settled long enough, you can see that yellow solid at the bottom, and then the solution sitting on top of it. And the solution kind of looks yellow and maybe a little bit because iodide ions have a little bit of a yellow tint to them. But there's also solid particles stuck to the side of the test tube, which is why it's also appearing yellow. Okay, so after you let this settle out, like you can kind of see the solid in the bottom right there, right down here. Okay, you'll have the precipitate right here. Okay, so yes, obviously lead 2 iodide would maybe be one you see a Ksp problem for because it is not very soluble in solution. Just do with it. If you remember, copper 2 plus ions are this beautiful blue color in solution. Okay, so this is copper 2 nitrate right here, solution of it. It's blue, it's beautiful. Okay, and so I'm going to put some in here. So there it is, totally transparent. Okay, it's blue, but it's transparent. Okay, and I'm going to mix it with some sodium hydroxide. So sodium hydroxide is another colorless aqueous solution. Hydroxides have limited solubility unless it's like with your alkali metals or like ammonium. But most hydroxides are not soluble, so you're going to see a precipitate form because the copper and the hydroxide hook up and make copper 2 hydroxide. I just like this one because it's a pretty color. So here we go. So right, 2 solutions, totally transparent. Okay. There's definitely chunks in there. Chunks is not the proper chemical term. It's solid, right? Okay. And I have some from leftover. So you can see the solid is at the bottom. Okay. When it has a chance to settle out. Let's see, I have another one. This one too. Solid has a chance to settle out. But definitely you see a precipitate has formed at the bottom. Okay, so copper 2 hydroxide is another example of a substance that might have limited solubility in solution, and you could see a Ksp problem for. Any questions on these so far?